Hello everyone, by the way. Glad to see you're on time today. Doesn't want to give. Okay, so let's read the article. Actually, no. Let me plug myself in first. So, a British scientist who was based in Australia in 1969 says he came up with the... Gary Peach, an engineer who was based in Tidbinbula tracking station near Canberra, said he was asked by his boss, who was in contact with the Apollo 11 mission, what he thought astronaut Neil Armstrong should say. Peach, now 73 and living in Berkshire, said, "One small step for our man, one giant leap for mankind." "I was worried about what would be said when they landed on the moon," Peach said of the landing. "I thought being Americans they might say, 'Holy chicken shit, look at that dust.' I felt it would not be a suitable thing to be quoted in history books for all alternatives." And Jack pointed out that Neil Armstrong flubbed the line because he said, "One small step for man, not for a man." Of course, so that means the small step and the large step were the same thing, if you leave out the "ah." That's quite funny. Okay, hello everyone, welcome to 1927, our second day of lectures. I'll make the slides bigger for you. And here we go. Okay. First of all, yesterday, do you remember? Now, he's not here today. His name started with D. What was it? Darren? Dylan, was it? Dylan, where are you? Where you're? Oh, no, it wasn't you that sorted them yesterday, was it? It was. Oh, okay. Well done. Dylan sorted using two algorithms, and we faced the general problem yesterday of given some data that wasn't sorted, that's a problem. How, not literally meaning how, but how in general, what's the algorithm, how can we sort the data to make it ordered? We haven't yet really addressed the question of why we might want it ordered or why this is an interesting problem to solve. At the moment, we're just going to view this problem like Darwin's finches. Remember, Darwin found millions and millions of unexpectedly large numbers of species of finches when he looked into it, when he started classifying them. We're similarly going to find there are an enormous number of algorithms to solve this one problem. So it's a very interesting example to pick to demonstrate the relationship between problems and algorithms. Now, my favourite guy of all time is Donald Knuth, and he's written some very fat computer science books. The Art of Computer Programming, Volume 1. The Art of Computer Programming, Volume 2. And The Art of Computer Programming, Volume 3. And he's at work on The Art of Computer Programming, Volume 4 at the moment, apparently, but I had a look on the website and I can't see any activity for the last couple of years, so I'm not sure how active that is. These books came out a long time ago and many editions of them have come out since, and they are still regarded as the Bible in algorithm design, and algorithm analysis. He's a very clever man, and what he brought to computing, or at least what he brought to me in my learning of computing, at the time I read these were really only the second time I'd ever read anything where someone approached computing in a systematic and analytical way, rather than just let's try this, let's try that sort of way. The first time I'd ever encountered that was when I read Dijkstra's book, A Discipline of Programming, which I also found quite moving and amazing. But these books surpass even that. Now the third volume, the first volume just talks about algorithms in general and ways of measuring and comparing and classifying algorithms and just gets us thinking about algorithms. The second book talks about what he calls semi-numerical algorithms, which are algorithms dealing with numbers, random numbers, computing with numbers, calculating numerical properties. Both these books are fairly general. The third book, just as fat as the first two, deals entirely with sorting and searching. Just essentially two problems, or in a sense they're almost the same problem. Or two problems, let's say two problems. So an entire book on two problems. This is because sorting is quite amazing. Just when you think you've thought of every way you could possibly ever sort something, well, just whenever I think that, I find a new way, and hear of a new way. I don't find it. When I was very, very young and programming my first computer, I was programming in BASIC on a machine that had 16K of memory, and I thought I was so lucky to have 16K when my friend only had 4K of memory. And it ran at some number of kilohertz. It was an incredibly slow machine, and it used BASIC. And I had been shown by someone the Bubblesort algorithm that Jarrah demonstrated to us yesterday. Remember, Bubblesort was the one that we actually acted out live. It involved a whole lot of tedious swapping. And surprisingly, because it wasn't intuitively obvious up front perhaps, surprisingly it ends up every single time with the sequence being sorted. And I saw it and I thought it was quite beautiful. It was really the first algorithm I'd seen, I guess. And I was so amazed by it that I tried to teach it to my younger brother. Now, he had only just learned how to program. He was a very little chap. And I said, Michael, your first challenge is this. Because I was a fairly obnoxious older brother. I want you to write something which, given an array of 10 numbers, sorts them into order. And I went away going, because Bubblesort is so obscure. I thought there was no chance he would ever stumble across this one algorithm to sort numbers. Once you see it, it's amazing. But coming up with it, he could never do it with his puny little brother brain. And so I went away, and when I came back, he'd finished. And he said, ta-da! Or in a 5-year-old voice, ta-da! Or something like that. And I said, ha ha ha, sweet little Michael. There's no way. And I looked at the code. That's not Bubblesort. That's not going to sort the numbers. And I ran it to prove to him how inferior he was. And the numbers were sorted. And I went, what? How has my brother, what's he done? He's invented a whole new way of sorting numbers. And now the world has two ways. And I wandered around for ages bragging to everyone about how bright my brother was and how he'd invented a new way of sorting numbers. And in fact, can anyone guess probably what he would have thought of?
You probably just said print 1, print 2, print 3.
Oh, no. It was given the numbers that were in the array. So not just printed out 10 arbitrary numbers in order, but given an array containing initially jumbled up numbers, not necessarily in sequence, return that array with those numbers rearranged so that they're now in ascending order. He didn't use insertion. He used selection. Selection sort, if you remember, is one where you scan through all the numbers for the biggest one, and then you remove it and put it in the right spot. Then you scan through the remaining numbers for the next biggest one, you remove it and put it in the right spot, and so on. And if you think about it, as a programming task, it's quite easy to do. You just have to keep track of the biggest you've seen so far, and then scan through the array, constantly updating biggest you've seen so far. Does that make sense? You can do it in fancier ways, but that will work. Yeah?
How old was your brother?
He was embarrassingly young. But he is not smart, and he is shorter than me. Okay, he claims otherwise, but he uses perspective in family photos in a really unfair way. So yeah. No, he's quite amazing actually. So, but selection sort is a natural sort of sort, and it's much more natural than Bubblesort. And for a long time, I was amazed. Before I had thought one problem corresponded to one algorithm. And it really opened my mind to think that one problem could have more than one algorithm to solve it. But for some reason, I didn't try myself and think of any others. I think I was satisfied to stop at 2. But as a scientist, I should have tried to generalize and work out how many more I could have thought of. And when I went to uni, I learned insertion sort, and then I knew 3. Now, these are the 3 sorts that people normally learn first. Bubblesort, selection sort, insertion sort. And they're the 3 we saw yesterday. But actually, they're all crap. It's quite surprising. I don't know why they're the first 3 we're taught. Particularly, I don't know why Bubblesort is the first one we're taught. It's counterintuitive. It runs like a dog. I can think of one redeeming feature for Bubblesort. Does anyone that remembers Bubblesort with all those millions of unnecessary swaps going on? What's the one redeeming feature? Yes, go in the back.
It's almost sorted as quick.
If it's, oh, 2 redeeming features. Well done. What's your name?
Chris.
Chris. Yeah, Chris is right. If the data is almost sorted, where almost we'll define more precisely next week for that particular case, well, let's define it precisely now. In fact, why don't you say it, Chris? What do you mean by almost sorted?
Well, if they're in reverse order, it's really bad.
Yes.
But if like the high ones are at one end and the low, then the right end, and a few swaps can get them there.
Yes. Yes. If the distance of every element from its desired position, if you find that maximum distance, then that's the most number of passes you need to do through a bubble sort. However, I better work out ups and downs. No, I think it probably works. It might be +1 or something, if the downs don't quite work out. I think that's, nah, let's forget about plus or minus 1, we're computer scientists. When's that ever going to hurt us? That's for a sort of bubble sort called bubble sort with early exit. If your bubble sort is smart enough to detect when the numbers are already sorted and stop, then bubble sort with early, which we call bubble sort with early exit will terminate quite quickly if the numbers are reasonably well sorted according to that definition of reasonably well sorted. However, most people when they implement bubble sort do something I would call oblivious bubble sort, which is it keeps going to the end, brute force, bloody-minded, regardless of if it's already sorted the numbers correctly halfway through. And that's the algorithm we were doing with Jarrah yesterday. Well, maybe he would have stopped eventually. Maybe, where are you, Jarrah? Once we'd done a complete pass with no swaps happening, so you knew that everything was in order, would you have stopped?
Of course not.
Good man. So that's oblivious Jarrah. Now let me move to another universe. Jarrah, would you have stopped?
Which universe are we in?
We're in the universe which contains Jarrah with early exit.
Oh. Yeah, I'll stop.
Yeah, he'll stop. So you see, it's quite clear what people would do. So we've got 2 different variants of bubble sort, but bubble sort, I think, has only one really redeeming property. Does anyone else want to have a hazard at what that redeeming property is?
It looks cool.
It looks obscure and can impress people. Yeah, that's right. There's nothing worse than when you do something really clever and then people look at it and they say, oh man, that's so obvious. Anyone could have done it. But in a sense, I'm going to claim, actually, they're the cleverest ideas. My theory is the cleverest ideas are so natural and so beautiful that when you see them, you go, oh yes. And it just seems so obvious that really you don't get any credit or praise. But somehow I think when that happens, you have thought of the most beautiful thing. Like da, 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 da. Yeah, yeah. Now we hear it, it's obvious. But coming up with it, before it was obvious, that's a different thing. Adam, you said something?
What's this have to, like,
Oh, what does this have to do with da, 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 da? We have moved a long way away from algorithms, thank you. But we have got to the idea of beauty and simplicity, and I think somehow the most clever things, when looked at through the right eyes, appear really simple and obvious. So bubble sort's obscure, yes. Bubble sort's counterintuitive, yes. Bubble sort has, however, one really redeeming property. Only ever stops adjacent elements in some particular memory configurations. That could be useful, yep. Someone, yep. Oh, sorry, the guy in front of you, actually. Was Jack in the back on John? I forgot. Chris, sorry, Chris. The guy in front of you, Chris. Let him have a go. Yeah.
it works?
It works. You can't underestimate the power of an algorithm that works. That's fantastic. It works, and actually, I'd say that's the right answer. But can I rephrase it in a way? Bubble sort is very easy to implement. It's just 3 or just a number of nested loops, depending on how you do it. It's very easy to implement, and when you implement it, it's going to work. With the other sorts that are more esoteric and fancy that we'll see over the next couple of weeks, you've got to think about them a little bit when you write them. And if you get them wrong, they won't work. So bubble sort has this beautiful power of sort of simplicity of implementation. Even though the idea behind the algorithm isn't so clear, the implementation is really clear.
What about I think it's postfix binary traversal. I can't remember which one it was now, but when he's traversing, it actually sorts it in order.
Yes, there are, yeah, Adam's mentioning another way of sorting. There are a bazillion ways of sorting, and that's one that's really good. And we'll see the family that class of sorting algorithms belongs to really soon. So that's right, there are millions of ways of sorting. Now what I should have done, and my homework for you guys is this. You solved my mistakes from my youth. Please go home tonight and think, without using Google, thinking actually meaning here rather than here. Think of how you could sort numbers. Think of an algorithm to sort numbers. Now maybe you're going to do it by picking up a deck of cards and dropping them on the floor and letting your very, very clever brain sort them, because we can all sort numbers. Anyone can sort a deck of cards. Maybe just do it and watch what you're doing and reflect on it, and maybe that'll teach you a new sorting algorithm. Or maybe just think about it in crazy ways and try and come up with new sorts. And when you've thought of one, then think of another, and then think of another. And maybe you can be as bright as my little brother. Maybe you'll invent a whole new way of sorting. I reckon if we sat down to think of it, between us all, we could probably come up with 10 or 20, without looking on Google, 10 or 20 really neat ways of sorting. But some of the neatest ways we probably wouldn't come up with unless we'd already seen. So we'll be seeing those in the next few days. But that's not your homework for tonight. I do want to challenge you to devise your own algorithm. Now, the ideas that we introduced yesterday were, first of all, the key idea of the course, that we're going to be classifying things in terms of P being problems, A being algorithms and data structures, because they go together. P being programs, processes, programs in motion, programs running. Okay, problem, sorting, we've seen 3 algorithms to solve it. We haven't written a program to do any of them yet. Had we done that, we could have run it and observed how long they took to run. The second idea we introduced yesterday was this notion of meaning. Just very quickly, remember we talked about one small step for man, one giant leap for mankind. And there's a link that talks about the mistake that Neil Armstrong made in saying the quote. And for a long time, actually, Neil Armstrong claimed he had said the word A. It just hadn't been recorded properly. And the reporters had misheard it. And then people played the tapes to him of the moon landing, and he said, maybe there's an A hiding in there. There's a little bit of crackle there, but eventually he confessed there wasn't an A. But for a long time, NASA had claimed that there really was an A in that audio tape, and he hadn't made a mistake, and we just couldn't hear it. And I'd like to think of that as what I'd call a dark A. So then we started talking, and the meaning idea was one small step for man being what you do, the mechanics. But in this course, we're more interested in the meaning, the giant leap, what this denotes. So really, whenever I talk about this course, I should really insert and meaning. This course is about data structures and algorithms and meaning. This course is about this and this and meaning. So can you just always insert that for me, because I'll always forget to say the and meaning. But that's really the important thing. All right, then we started talking about science, because the word science appears in the phrase computer science. And I showed you some movies about science, which I showed to my daughter to show how wonderful science was. And lo and behold, I discovered when I showed her all those movies last night that in every single one of them, scientists were depicted as evil and bad. And it was common, everyday, decent people. And isn't that funny, the world's view of science? I think it might arise from the Manhattan Project, maybe. But somehow for a while we thought science was magnificent, and now we're very skeptical of it. But I don't think science is all bad, so we sat down to think, what is science? And maybe we can take some good ideas from science. And I challenged you to tell me what science was, and we got lots of suggestions from you guys. And interestingly, they all fell into the category, I think there are 3 sorts of ways of answering this question, which I've written down here, of notions of truth. You all told me what it meant to have scientific truth. Scientific truth versus religious truth versus legal truth. Legal truth is balance of probabilities or beyond reasonable doubt, depending on whether you're doing civil or criminal matters. Engineering truth is within the bounds and limits of measurement error. Mathematical truth is I can prove this using the axioms that we accept and the proof methods we accept. Religious truth is it's written in some authoritative book somewhere and hence it's true. I'm sure English truth might be, like literature truth might be, I look at it, it's beautiful, it's true, maybe. I don't know. Every discipline has its notion of truth, and we saw that truth in science was really about constantly trying to prove that whatever we were talking about as being true wasn't true. This act of trying to disprove what we wanted to believe. And this is called falsification, and I would like to summarize that as skepticism. And I think, as computer scientists, I hope, as students in fact at uni, I hope you do develop skepticism. I think that's really important. And certainly you shouldn't believe everything I say, because sometimes I might say things that aren't right by just sheer accident. So not everything I say is true, and not everything that anyone says is true. So I hope you all develop skepticism, and I hope with your programs you develop skepticism. And when you write a program, you don't just think, oh, it's correct, but you try really hard to prove that your program has a mistake in it. And if you fail to prove it has a mistake in it, I hope you don't relax and say, oh, I've finished, I can go away. I hope you think, oh, I haven't proved hard enough. and you try again. And I hope computer science to you follows this notion of constantly trying to prove your programs wrong. And we have, what's that again?
That's sort of like desk checking.
It's like desk checking. We have a name for it actually in this course. It's our unit testing methodology. So does everyone know the unit testing methodology we follow in the course? Did Maury drill that into you over and over again? Someone tell me how we do unit testing. That's the small step sort of description. That's what you do, but I want to know what does the process involve of unit testing? What are the key things? Yes?
You get a bunch of different tests and run them against different small sections of your code.
Yes. When do you write the tests?
Before you begin.
Thank you. So we write tests before we begin. We form our hypothesis before we begin. We work out our method before we start. We write our code. We run the tests against it. If everything works, we're happy, we keep programming. If we find more mistakes, we write a test to demonstrate that that mistake is in our code. We add that test to our test suite. And every time we make any change to our program, we run the entire suite of tests. We never throw a test away. We run the entire suite of tests against our new program. So by the end of a long development, if you've been working on an assignment for 3 weeks, your pile of tests might have grown to several hundred tests. And every time you make a change, you go, run the test version against it, and it runs those full 100 tests against it, and you're hoping it's going to say, bing, yes, correct. So that's the sort of skepticism I'd like to see. But that's not why I'm going to say computer science is like science. So although you all jumped to that one first, notions of truth, someone pointed out, probably from a notions of truth point of view, computer science is probably closer to maths. The notion of science that I think we can steal and make good use of in computer science is this notion of abstraction, which is, I like to call it the most important thing, which is when we're faced with a problem, we try and work out what the most important thing about the problem is, and we just focus on that. And it doesn't matter if you get the other things wrong, but if you get the most important thing right. So another way of saying the most important thing is we abstract away the things that aren't the most important thing and we just focus on the most important thing. And that necessarily leads to classification. So given anything, we try and classify it by its most important property so we can more sensibly think about it. And that's what we're going to do with algorithms. We're going to somehow work out what the most important things about algorithms are, and then we're going to classify our algorithms in that way so we can start talking about classes of algorithms sensibly. And the last thing I think of that we can draw from science, that where computer science can benefit from science, is just the habits of being a scientist. Scientists tend to be quite ordered and systematic and methodical in what they do. And I think that's what we should do. So Rupert and I, for example, were testing something today that wasn't quite working. And we realized what we had to do was write down first exactly what all the problems were and what we were going to do and write down our method, and then log as we did each change what we did and record the results and go through it systematically, rather than just randomly trying changes, as you yourself probably do when you try and debug a problem. Sometimes that will expose the problem straight away and you can move on. But if it's a hard problem and just fooling around with it for a while doesn't solve it, then a systematic approach, like a divide and conquer approach, like a quartering the field that we're searching, like the police do when they're searching for evidence. Rather than just wandering around the field constantly looking for evidence, they quarter it, they divide it into small sections, they mark them on a map, and then they systematically search each section really thoroughly before moving on to the next. This way of approaching things systematically can help us when we're stuck and don't know how to proceed. So I like the habits of a scientist, and I hope in this course we'll develop those. And I have a geeky song here that demonstrates, I think, the habits of a scientist. And this is geeky song number 2 because we did a geeky song yesterday. And I've got this idea that maybe we could even find more geeky songs. Has everyone seen this one? Oh. Of course, it's normally louder than that. Oh no, now we can't hear it. Gee, I don't know what I did then. It's a... Okay, so it's a group of mathematicians singing about love, and they're talking about a finite order group of 2, and that's like obviously him and his partner. But now the interesting thing in this song happens at 2 minutes 20 seconds. It's a little joke they make. Okay. So they're in the middle of singing this song about they're a finite simple group of order 2. And suddenly the guy at the back says, why not 3? And that's sort of funny for like innuendo reasons. But I think the reason the mathematicians were laughing at that is how we're supposed to think as a mathematician and a scientist. If someone says something and there's some special group and it's special and it's of order 2, the right question is to always try and generalize and not just say, oh, I believe you, it's order 2. You say, wouldn't a finite group of order 3 solve this just as well? So why not 3? That's the right question. So I think the idea is when we see something, we don't just accept it, we try and generalize. And I think that's a good habit of a scientist. For example, if Harry Potter was a scientist, in one of the Harry Potter movies, I saw the time, they go back in time. Has anyone seen that? So Harry Potter and his friends are doing something lame that doesn't make sense at the time. And then 10 minutes later, they've gone back in time and they're standing in the trees looking at the house, and suddenly Harry Potter walks out and he goes, oh, that's me. And there he is behind the tree looking at himself. That's right. Essentially. Now, if he was a mathematician, what would he have done? If he was a scientist, if he was you guys, had your analytical brains? It's interesting that he is sitting there watching himself, and he himself doesn't know he's being watched.
Look behind him.
Look behind him! Yes! That's the right thing to do. Oh, it's possible to have multiple copies of me observing myself. That's interesting. This is the sort of thinking that we want you to encourage. So I think scientific thinking is absolutely wonderful. It won't necessarily give you the right result, but I think it's a really neat approach to problems that can often be fruitful. Okay, so that's our summary of everything we've done so far. Now let's return to classifying algorithms. We're about to classify our algorithms. We've got our problem. We have many algorithms that solve that problem. We saw yesterday that we have to classify them based on observable properties, and yes, we straight away had correctness. They have to be correct. We'll just take that for granted now. And we thought maybe it could be based on speed. We're interested in how long the program takes to run. We can observe that. And maybe we're also interested in how much memory the program uses. That's also an externally observable thing, in that your program will fail if there's insufficient memory. So let's think about classifying. Now, it's going to turn out that we're going to classify them in the same way. I'll just look at speed for a while, but once we've dealt with speed, memory will be exactly identical. And this classification technique we're going to use is called complexity. And when I talk about the complexity of an algorithm, I'm normally just meaning the time complexity, but sometimes I actually mean the space complexity. So you might want to grill me if I'm being vague, because they're so similar and closely allied, and they use the same ideas. So complexity is the technique we're going to use. Now, I have a video from yesterday. Oh, that's great. So remember yesterday we ran out of time because we were so completely not very organized. And we had, if I can just cast your mind back to yesterday, suppose you're watching us yesterday. This is time travel. Okay. Good man. We had here Thurston's old T something or other, which ran at 8 megahertz. It was selectable to 4.77, but we couldn't work how to do that. That would have been fun. So it was a crappy old machine with an LCD monochrome screen that ran at 8 megahertz. It was a 286 16-bit microprocessor. It was completely stuffed. And then we had my incredible Macintosh here, faster than the speed of light, more expensive than the speed of light. And we had the same problem, and the problem we were trying to solve was how many comparisons does an oblivious sort do? An oblivious quicksort. And we discovered that an oblivious quicksort does, if it's sorting n things, does n minus 1 comparisons the first time, n minus 2 the second, n minus 3 the so, and we added that up. It's just an AP, we added them up, and we found that the sum was n outside of n plus 1 divided by 2. So if I told you I'm sorting, it's actually, I'm out by 1 there, aren't I? Because if we're sorting n things, we do 1 less comparison the first time. So it's n outside of n minus 1 divided by 2. Can someone double check? That's right. Yeah, it's n outside of n minus 1 divided by 2. So if you were comparing 2 things, you do 1 sort. Well, I'm a computer scientist. What should I start with? 0. Yeah. If I'm comparing 0 things, I do 0 sorts, 0 comparisons. If I'm comparing 1 thing, I only have to do 0 comparisons. If I'm comparing 2 things, I do 1 comparison. If I'm comparing 3 things, I do 2 comparisons plus 1, I do 3 comparisons. So if I could imagine I had a function. I stick in the number of things I'm doing, n, and it puts out the number of comparisons I'm going to do, which will be n outside of n minus 1 on 2. And you could tabulate that for a range of values of n, and you would find that sometimes, just by sheer coincidence, the output you'll get would actually be square numbers. Now, there's nothing special about this. It's just an arbitrary thing we picked, because it only happens occasionally. Sometimes they're square numbers. So, for example, when 1 came out, it was a square number. And we found we could get 36 coming out. That was a square number. And I thought, wouldn't it be fun to have a program that listed for what values of n you get a square number coming out here? And I wrote a program in C to do that. And here's the program here. Let's just have a look at it. Oh, my laptop is thinking this is a second desktop. That's going to be confusing. I'll tell it to mirror everything. It's a very intelligent laptop. Look at that. There we go. So here's my C program. What it does is it starts with, it reads in the number of argv. The first argument I give it will be the number, will be the input n. It creates a number called n. It sets it to be a new number, which is 0. Creates a sum to n from 0 to n, and sets that to be 0 initially. It finds the number of squares it's found and sets that to be 0. And then until the found is the desired count, so if I say find me the third number that's a square, it'll keep looping until it's found 3 of them. Until the number we've found is the desired number we want to find, keep looping. And all it does each time is add n to the sum. So the sum gets bigger each time. It adds 1, then it adds on 2 the next time, then it adds on 3 the next time, and it adds on 4 the next time. Yep, so it's getting the sum from 0 to n. And then it's checking to see if it's a square by this function called isSquare. And if it is a square, it says it's found it, and it prints it out. And if it isn't, it doesn't print anything. And no matter what, it then increases to the next value of n. And it scans through until it's found the right number of them. And if you just wanted to run it, can we run it? I think I had a window somewhere that would run it. Here we are. If I said big squares, print out the first 4, it'll print out the first 4. And if I say big squares, print out the first 10, it prints out the first 10. Does that make sense? And it's just looking for them one at a time. That's one way of solving that problem. The code I've just shown you then, Richard's code, is an implementation of Richard's algorithm, which is just searching one at a time. We sometimes call that a brute force search, which solves the original problem of which ones are squared. But there is a second algorithm. Well, there are many algorithms you can use to solve this problem. The second algorithm gives rise to different code. We first implemented the second algorithm on his computer. He wrote it in BASIC, so as a program, not only was it implementing a different algorithm, it was implementing a different language. And then we ran it on a different machine. So as a process, it was quite different. My machine, super fast. I think it runs at 100 million gigahertz. And his machine ran at 8 megahertz. Yeah, you can get little microcontrollers. Someone I met the other day laughed when he saw Thurston's machine and said, my little microcontroller that costs 20 cents is twice as fast as that.
There's one that has like 8 cores and 60 watts.
Yeah, it's amazing. So his machine is just worth so little, but on the other hand, it is a very beautiful machine. Okay, so this is our setup. Everyone sees it. Now, what did we find yesterday? Well, we ran out of time, so immediately after the lecture, Thurston and Rupert and I went up the top and we videoed it. We ran the machines next to each other in a head-to-head competition and we made a video of it. And let me show you that. It's in no name. Here we go. I don't know if it's got audio. So here are the two computers. On this side, the Toshiba. On this side, the MacBook. You can't hear it, so I'll just do the voiceover myself. Here we have the Toshiba. Isn't it beautiful? Notice it's written in BASIC. There's its keyboard. Isn't it beautiful? Here's the name of it to prove it really is Toshiba. The /20 means you can upgrade the hard drive to 20 megabytes. Though Thurston never did that because he didn't have the money. Here's my laptop. A bazillion megabytes. It's very fast. It has the ding-ding corner where I dropped it the day I bought it. You can see it's going to run it for 15. Go. Print out the first 15. On your marks. Get set. Go. Print out the first 15. No, we're not going to print out the first 15. That would be crazy. Let's just print out the first 9. Thurston changes his over here to be 9. Can you see? And we're about to run them. On your marks. Get set. And there... Oh, there's Thurston. Proof it's Thurston. There's the finger. It was more exciting when we did it. Go! Oh, it's finished. And Thurston's is still printing them out. Proof that my money was well spent. But lo, now we're going to run it for what, 11? Oh, and he's still going, and oh, it's taking me a little while to find the 11th, but still I found it, and he's only up to 10. And then we're going to clear the screen and run it for, what do you think, 12. Go! And here we are, 10. I'm at 10. He's on at 7, 8, 9. I'm at 11, 10, 11. Oh, he's done 11. 12. What? Less powerful than 20 cents, that machine. Get a Mac. Everyone there, fantastic. I love it. Still waiting, still waiting. Still, I thought you'd like to watch it. Ah, it's finished. Okay. So then we said, okay, maybe that was an anomaly. Let's run it for 15. On your marks. Oh, on your marks. Get set. By the way, this is basic. It's running in DOS 3.1. And it's running basic, which is crap. There we are, 11. He's going 9, 10, 11. This is Rupert zooming in just to rub it in. 12, 13, 14, 15. My algorithm, which is just that program I showed you a second ago, still stuck on 11. It eventually went to 12. I ran it for a couple more hours, and it went to 13. I left it running constantly between then and now, and it never, ever got to 14. Okay. So, yeah, can we just applaud the documentary makers? Who are actually up the back. Thank you, guys. Yeah, question?
Could your Mac have been sort of slow because it's a preemptive multitasking and it like only gives it like 100 milliseconds at a time or something, or the DOS just gives it?
There are a series of things that might have made a small difference to the machine, my machine. It might have been doing some memory management in the background. It's got a 2-core machine. I tried to get all the other processes and the system stuff happening on the other core, so this had a whole core to itself, but I might not have got that right. So yeah, and the way the operating system does a bit of house cleaning, and it's running an indexing service in the background. So there's a range of things that might have made a slight difference to the speed. And Thurston had a hairdryer on his, heating it up to get an unfair turbo boost. But I claim that those small differences are not going to be relevant. Let's have a look why. Let me just give you some light. His machine took about a second to do each one. Well, actually, we can actually probably measure it just by dragging this meter along here. There's 13 appears at how many seconds? I was not displaying it. Oh, you can't see it. Oh, I can see it. Let me just count. Can you guys count? Does someone have a stopwatch? What? The time is just, oh yeah, thank you, 2:20. 2:20 is when it hasn't started. And it's more accurate if I do it over a large range of numbers. 15 took to 36. So it took essentially 16 seconds. Let's say 15 seconds. So his algorithm did 1 in 1 second. 2 in 2 seconds. Did 3 in 3 seconds. Did 4 in 4 seconds. Did 5 in 5 seconds. Now mine did 6, let's keep going, in 6 seconds. 7 in 7 seconds. 8 in, I just like it when lecturing's easy like this. I might not stop. 8 in 8 seconds, 9 in 9 seconds, 10 in, not that easy, 10 seconds, 11 in 11 seconds, 12 in 12 seconds, 13 in 13 seconds. Mine, on the other hand, did 1 in something like 0.00001 of a second. And this also took about 0.00001 of a second, you know, just below the bounds of being able to measure. 0.0001, 0.0001, 0.0001, 0.0001, 0.0002, 0.000 1, 0.01, 0.1, about 1. Am I right or am I out a bit? I'm out a bit, thanks. Still I'm out a bit? Yeah, that's right. Oh no, it got bigger than that even. It takes more than 10 times each time. I'm just trying to get it right. The point is, if I'd been able to speed up my machine by optimizing it in some way and getting a 20% speed up, which would be pretty remarkable by just fiddling the settings on the machine, instead of taking 10 seconds, it would have taken 8. And instead of taking 100, it would have taken 80. And instead of taking 10,000, it would have taken 8,000. Can you see 8,000, 10,000, who cares? Thurston could do it in 13 seconds. This is what I meant when I said the most important thing. In first year, first course, I sometimes set race assignments where students have to write code to race against other students and against the tutors and against me. And the students invariably, especially the really, really smart, experienced programmers, spend all their time doing small optimizations. Because they know, oh, if I do this, it'll get stored in page memory rather than this memory, and that'll save me 0.5%. And if I do this, it'll just do this. And in fact, I once at a lecture asked the first years, in the first course, you guys are like 1.5 years, what can we do to speed up our programs? And one of the smartest guys in the room stuck up his hand. Let's say it was you. What? What is it? You've forgotten now.
Algorithm.
Oh, you are the smartest guy in the room. Yeah, yeah. He stuck up his hand and he said, you could take the comments out. Because at that time we were writing in an interpreted language called Haskell. And the compiler does take the interpreter took a split second, presumably, to jump over the commented out lines. So he might have saved a millisecond over the whole run of the whole program. But it's true. So he had to be very clever to think of that, but it was stupid. He wasn't thinking of the most important thing, he was just thinking of the thing. The most important thing, he then changed his mind to be
The algorithm.
the algorithm. The algorithm kills everything. I don't care what machine you run it on. At work, you'll be running something, it won't be fast enough, and your boss will say, let's buy a faster machine. Let's get a supercomputer. Let's get one with more cores. Let's get 1,000 cores. It's irrelevant. Okay? They'll say, let's write it in C rather than in Java because C is faster than Java. Sure, by a factor of 3, it's irrelevant because the difference between picking the right algorithm and the wrong algorithm is not a factor of 3. If we kept going here and I got down to 20, it'd be over a factor of 1,000,000. So I don't really care if you get a factor of 3 speed up. It's quite nice, but I'm impressed if you get a factor of 100 or 1,000 or 1,000,000. So when we run races and I put my entry into the races, what I do is, because I am at heart a hacker and a geek, test because I look so cool that I'm actually a geek. What I always do is I instantly think of all these really hacky things I could do that would give me a 1% speed up. And I just can't resist. All I can do is think of them. So I write them down on a piece of paper to sort of set my conscience at ease. I write them all down. I say, I'll just write them down so I won't forget them. Don't worry, brain, I'm listening to you. And I write them all down. And then I think, okay, I'll do those later. And I make sure at the top of the list I put the most important thing. And the most important thing is pick the right algorithm. And after you've picked the right algorithm, you'll get 100 times speed up or 1,000 times speed up or 1,000,000 times speed up. Then I go down that list and maybe I get a 2% increase in a one. Maybe I don't even bother going down that list. Does that make sense? You will be facing a race for your second assignment. Please do not spend all your time fiddling with 1% and 2% increases. That's just what we call hacking. That's fiddling. You're fiddling around at the, I've rubbed it out. You're fiddling around here, or you're fiddling around here. If you can fiddle around here, and you can't always, but if you can fiddle around here, it makes an astonishing difference. So go for the most important thing first, and often that will be the algorithm. Now actually, there's something even better than fiddling around here. Can anyone guess what it might be? For really hard problems. Change the problem. If you can do it. And was that what you were going to say?
Not really.
I think changing the problem can kill everything. I once had a boss that used to set me impossible problems, and one day I had the courage to go to his office after he'd given me this really hard problem. I said, would you mind if I just did this instead? And he said, yeah, whatever. And it changed from like a 3-month programming job to a 10-second programming job, because the thing that he didn't care about was the thing that was a really... So sometimes you can replace a problem with a problem that's nearly as good to solve or does the trick, and that's fantastic. But if you can't change the problem, well then make sure you pick the right... Once you've got the right algorithm, sure, put all the other speed-ups in that you can, but the algorithm's a killer. Okay, now I think we'll have a little break now for 10 minutes, and then we'll return and we'll start looking at some algorithms in particular, and we'll start classifying some algorithms so you can see.